the planet's oceans can often be a perilous place to work. Waves, wind, and rain make building something at sea one of the most challenging and dangerous engineering tasks around. Overcoming this hostile environment takes a vessel with some extraordinary capabilities. Enter the Sleipnir. Named after a mythical 8-legged stallion ridden by a Norse god, it's a 154,000-ton heavy lifting crane megaship that's redefining how we build at sea.
Sleipnir is the biggest semi-submersible crane vessel in the world. Not only in size, length or width, but also lifting capacity. We have two of the biggest cranes in the world on board. That makes it the biggest and the baddest.
I believe that the Sleipnir is absolutely one of the most complex things ever built floating at sea. It's big, it's strong, it's fabulous.
Longer than 3 A380 passenger jets parked nose to tail, and wider than the Statue of Liberty laid on its side. Beneath the surface, 8 gigantic thrusters propel it through the water. While almost 165 feet above, on the 130,000 square foot reinforced deck, sits its crowning glory. 2 record-breaking cranes, each capable of shifting the equivalent weight of the Eiffel Tower, allow the Sleipnir to build or decommission oil and gas platforms, as well as install gigantic wind turbines, all while floating at sea.
We are now in the central control room. On all ships you would call this the bridge. From here we control navigation, dynamic positioning, ballasting, safety, fire alarms, and it is the communications hub of the ship.
It's the responsibility of Captain Arjan Udo to ensure the safety of the supersized ship and the 400 workers who live on board.
Sailing this ship is different from normal ships. We're one of the widest ships in the world. She's very high. Sometimes we call it an apartment building. Only it's a really fast apartment building. The sailing in itself is not difficult. It is all the other vessels around you that you need to keep an eye on. And that's ferries crossing, people in sailboats, sometimes an idiot in a rowboat. Anything can happen. All you have to do is watch out the window and don't run into things.
With a top speed of around 14 miles an hour, this floating behemoth can cross the Atlantic in less than a week, thanks to an innovative fuel system hidden deep inside its 8 giant columns.
At the moment we are in one of the LNG tank rooms. Our fuel, the LNG, is contained inside this tank at minus 160 degrees Celsius.
This is the largest vessel capable of running on either traditional marine diesel or liquefied natural gas, known as LNG. For Joris Velders and his team, this industry first means all new challenges.
Fuel tanks like these have to be kept at a low temperature due to the fact that the natural gas in nature is a gaseous form, and we have to condense it into a liquid to reduce the storage capacity. For an example, 1 liter of liquid gas exposed in gaseous form to 600 liters of gas.
But keeping a super cold liquid secure while floating in the middle of the ocean isn't an easy task.
Looking upstairs, we can see that there are wooden blocks. We used wood to prevent the minus 160 degrees radiating outside to the vessel structure. Because the vessel structure, if it is touched with minus 160 liquid, it will become brittle. Okay.
With the vessel currently empty of fuel, Joris and his team have a rare opportunity to venture where very few people have or will ever go.
We are currently in the LNG tank. This is a unique opportunity. Normally in this area you have 1,000 cubic meters of liquid gas at minus 160 degrees Celsius. Downstairs, 2 of my men are dismantling 1 pump for periodical maintenance. The tank is 8 meters in diameter and 25 meters high. Where we're looking at is about 23 meters deep in the dungeons.
Out on the deck, a large proportion of the electricity generated by burning the LNG will be consumed by the ship's 2 gigantic cranes, designed in part by Specialist Technical Superintendent Jori Brouwers.
So here you have a complete overview of the crane. The top of the A-frame is 125 meters above the water, and if the boom is fully up, it's 170 meters high.
Ja, komt ie.
This whole crane is only operated by 1 man.
How many meter average? 60.
Okay, 60 meters.
He's sitting in a control cabin connected to the crane, so he has a good overview of everything. It's really amazing engineering.
However, creating such a vast vessel poses many seemingly impossible engineering challenges. How can a floating structure remain upright as it lifts the equivalent of 35 passenger jets into the air?
To design and build a vessel that can lift 20,000 tons is one of the most difficult things in the world. I think you can compare it to sending someone into space.
How do you engineer a crane that can rotate even with a load attached?
The loads that occur on the structure, they are immense.
And keep up to 400 workers safe as they carry out some of the most dangerous tasks on the planet.
You have big waves, lots of wind, so it's really a difficult environment to do these type of jobs.
To achieve this, engineers will need to draw on inspiration from the pioneers of the past.
Wow, look at it. What an amazing piece of technology.
Here it goes. This is a beautiful system, but it has one problem. The door is closed. Oh, I'm so nervous.
This is the Sleipnir. The largest heavy lift crane vessel in the world. Designed to shift gigantic pieces of energy-generating infrastructure. Its 2 record-breaking cranes make it unlike anything else at sea. Weighing roughly 150,000 tons, it's 10 times heavier than the Brooklyn Bridge. And from the waterline to the top of its cranes, it stands more than 230 feet taller than the London Eye. But propelling a vessel of such monumental proportions through the water is an enormous challenge.
When you're sailing or want to go sailing, you need to increase power. Now, all the equipment here is big. This thruster is 5.5 megawatts, which is about 8,000 horsepower. You have 8 of those. They are being fed electricity from the generators. Those are 12,000 horsepower each. Now, Sleipnir is the most powerful vessel I've ever sailed on, that's for sure.
Below the central control center, deep inside the main deck, are the Sleipnir's 4 engine rooms.
Hey, can you start engine number 10? Because we need more power. Thank you. Now the pre-lubrication systems are starting, and then the engine will come online.
And it's up to engineer Joris Velders to ensure that there's always enough power to go around.
Beautiful. Very good. Back. We are currently standing in engine room number 4. This is nice, running, spinning. In each engine room we have 3 diesel engines with driver generator. Each engine is good for 8,000 kilowatts. And all together we have sufficient power to provide a quarter of the city of Amsterdam for power. The electrical power is used to propel the vessel, to operate the cranes. We have accommodation for 400 people that also need electricity. For example, your toothbrush will also be powered via this electricity.
Engineers may have found the solution to propelling this mega ship across the ocean. But once the Sleipnir and its army of workers get to their destination, how do they safely lift over 20,000 tons without a solid foundation? It's an enormous challenge for the ship's designers, headed up by naval architect Sipke Sherman.
When you're in the middle of the ocean, of course, you're exposed to big waves, lots of wind, current. So when you lift a big load, you want to avoid any damage. And you avoid damage by reducing the motions. How do you do that? Well, you have to have something floating and stable, of course, because if you lift something, then it wants to capsize. Also, you lift it at a point very high up, so the vessel wants to tip over, so you have to provide stability. Those are the kind of things you have to take into account.
To keep a vessel upright in the water while it lifts loads up to 22,000 tons is a monumental challenge.
Potentially you capsize, and that's really what you want to avoid.
To find a solution, the Sleipnir's engineers must look to the innovations of the past. Engineer Sascha Koschlik is in the northern German shipbuilding city of Rostock.
Well, just look at all the cranes over there. They come in all shapes and sizes.
Discovering an innovative piece of maritime engineering.
Wow, look at it. What an amazing piece of technology.
This is the 177-foot-tall Long Henry, or Langer Heinrich as it's known to the locals.
I've never seen it from that angle, from the water. That's just amazing.
One of the oldest surviving floating cranes in the world, it was revolutionary for the time. Designed in 1905 by German engineers August Beschem and Theodor Keetmann, the Long Henry's arched shape allowed it to reach further than other cranes of the time, while an ingenious system hidden deep within its pontoon allows it to lift 100 tons without capsizing. To demonstrate, Sascha has prepared an experiment.
Now here I've got my crane attached to a pontoon, just like in the background with the Langer Heinrich. And if we put that in the water now, like this, it's floating nicely upright, it's perfectly balanced, right? But if I put a little bit of weight onto the boom, and I've got here prepared a little bucket with some rocks in here, if I attach that, then the whole thing will just tilt over. And it will end up in a complete disaster, as you can imagine here, right? So what can we do in order to counterbalance it again? We need to put weight onto that side of the vessel. And what better is there to use than actually the water in which we float? So I've prepared here 2 ballast tanks, basically. One that is only partially filled, that goes onto the front. And we've got one which is almost filled, that goes onto the back of the vessel. So we put that here, and the other one goes right here. Here we go. So if I now add the load to the front, what we can see is it floats upright and it's nicely balanced. And that's exactly what they do in the Langer Heinrich.
On board, 9 ballast tanks hidden deep inside the pontoon of the Long Henry can be filled with over 200 tons of ballast water.
Wow, this is amazing. We're now right in the belly of the crane. We've got ballast tanks behind those walls on either side, and everything was done by that tiny little pump here on the side, which has 1 horsepower actually. And with all those pipes you can see here, you could move the ballast water to either side of the vessel, depending on what you actually wanted to lift.
Having served in shipyards in Poland and Germany, and after over 7 decades of service, the Long Henry was finally retired.
It's quite amazing to think that it has worked throughout the 2 world wars and has been shipped around Europe. And yet here it is, still floating, and when you look at it, it looks almost as good as it did the day it was built.
Back in the Netherlands, engineers have taken the concept behind the Long Henry and enlarged it to astronomical proportions.
Sleipnir is the biggest crane vessel on Earth. It's 100 meters wide, 220 meters long, and to the top of the crane, 200 meters high. The size of it, it's really amazing.
To ensure it doesn't capsize during a lift, engineers have designed an equally supersized solution to balance the load.
It's the semi-submersible, and you can see that see his columns, and we can sink it down to about 30 meters draft.
Underneath the waterline sit the ship's 2 giant pontoons. Inside them, 82 ballast tanks can be pumped full of water, adding more than the weight of an aircraft carrier to the vessel and sinking it to a maximum depth of almost 120 feet.
The deeper it sits, the more stable it gets. And also when we lift big weights, we need to have counterballast basically, which we do with water ballast.
Once the team is out in the middle of the ocean, it's the responsibility of Captain Arjan Udo to ensure that this process runs smoothly.
This is where we do all ballast operations for the whole vessel. What you see here is an overview of the port side of the ship and then the ballast system. So you see tanks, pipelines, and here you have what we call the pump room with the ballast pumps. And the ballast pumps we use to get water in and out of the ship. And now we are 140 million kilos. When we're at working draft, 32 meters, it's almost 300 million kilos. That makes the ship more stable for the lift operations. The ballast system on the Sleipnir is designed big, actually so big that we can fill an Olympic-sized swimming pool inside 5 minutes.
In total, Captain Udo can pump on board almost 210,000 tons of seawater.
But this ship has a party trick, and that is our dynamic ballast system. We can use it to balance the loads that we pick up better. And basically, you have a connection in the hull, water comes in, you use the pump to put it on the right location, open the same valve, and you discharge a lot of weight very quickly. And that means we can use the ballast to balance the loads on the vessel better.
On board, 16 dynamic tanks allow the Sleipnir to continuously adjust its weight.
Ballasting is controlled sinking. Sinking is something you tend to avoid on a ship. It always gives you a weird feeling.
This sophisticated system is key to Sleipnir's lifting capacity. But it's just one of many creative solutions necessary to make this one-of-a-kind vessel sail. To overcome some monumental challenges,
Lifting a load is only half of the battle.
engineers will look to innovators of the past.
The world around us will be a very different place without this ingenious component.
Heerema Sleipnir is a marvel of engineering. The largest ship crane in the world, capable of lifting the weight of 20,000 cars at once. The vessel's dynamic ballast system allows operators to finely tune depth and stability as they handle some of the largest lifts in the world. Many decks below the control center, deep inside one of the giant pontoons.
We'll do an inspection. Yes? Okay.
It's up to engineer Joris Velders to ensure that this controlled sinking system is in perfect working order.
At the moment, we are in one of the ballast tanks of the Sleipnir. The particular ballast tank is one of the biggest, and it is about 6,000 cubic meters in size. And to give you a reference, this comparison would be 2 times an Olympic swimming pool. It's unbelievable. There are a few ways to fill it up. You can do it with free flooding by just opening the valves, and then by gravity they fill up. And we also have 8 ballast pumps, and these pumps can also, at high speed, fill it up. And getting the vessel empty to get it at sailing draft again, we use the same pumps to pump it out again. This vessel, when sailing, has a draft of around 12 meters. If we are doing normal operations, we can go to 32 meters.
The dynamic ballast system maintains vertical stability, but Captain Udo and his team also need to maintain Sleipnir's geographic orientation once the enormous vessel is in place.
At sea, you have influence on the ship. You have wind, you have waves, you have current. That tends to move the ship. But when you're building a platform, you want to stay in the same position.
To do this, they rely on advanced GPS and sensor information.
We keep the Sleipnir in position by handing control of the thrusters to a computer system. So it calculates forces on the ship, and then it calculates a solution, how it should get from where it is to where it needs to be. The accuracy of this system on a ship of this size is within 30 centimeters. If there's a bit more wind, maybe 50 centimeters. It stays within that footprint for weeks on end if you want to.
But once in position and ready to lift, the team faces another challenge. The ship's 2 vast cranes need to be able to rotate 360 degrees, even with over 10,000 tons hanging from them. It's up to Technical Superintendent Jori Brouwers to find a solution.
So to lift 10,000 ton is even more impressive if you consider the forces that occur on the structure. They are immense. Lifting a load is only half of the battle. When you have the load lifted, you also need to be able to rotate the cranes to position the load where you want to put it.
So how do you rotate a crane with such a heavy load attached? Could a solution be found in the innovations of the past?
All right, take her up, Paul.
Physicist Susie Sheehy is in the heart of the English countryside, finding out if she's got what it takes to be a miller.
Wow, well, it's a great view up here. I can really feel the wind when I get up this high.
And discovering an engineering solution hidden in an unlikely location.
So on these big structures, these ribs, I'm going to try and put one of these enormous canvas sails so that the windmill can catch the wind.
Built in 1632, Chesterton Mill is one of the oldest operating examples left in the country.
The sails are ready, the wind is up, so I think we're going to give it a spin. So Paul, can we head back up? Thank you. I'm really excited to see this turn, actually. Oh, here it goes. So at the moment, the wind is coming in, it's hitting the sails, they're tilted at a slight angle, and that creates this turning motion, which is really quite beautiful. But it has one problem, and that is as soon as the wind changes direction, it's going to grind to a halt. So what we're going to need to do is change the direction of the windmill so that we can pick up the wind again and keep going.
But how do you rotate a structure that's fixed firmly to the ground? The solution lies in an ancient innovation. In 1588, Italian engineer Agostino Ramelli published designs for over 100 devices capable of pumping or raising water from wells. And deep in his sketches lies the solution to the wind problem faced by the engineers at Chesterton Mill.
Oh, wow. Oh, this is great. So I'm now right at the top of the windmill structure, and over my head is the cap. To get it operating in an optimal way, we need as much wind as possible.
which means we need to rotate the cap towards the direction of wind. But that's not going to be easy because this is a massive, heavy wooden structure.
Weighing a whopping 8 tons, rotating the cap is only possible thanks to Ramelli's ingenious solution.
So the way it works is there are 2 rings around the outside, one here attached to the cap on the roof and one attached to the mill, and in between are the rollers. So what this system allows is that the cap, which is circular, can rotate while the mill stays still.
Inside the cap, the giant wooden roller bearing connects into a system of gears that allow the miller to manually rotate the position of the sails, ensuring no matter what direction the wind is blowing, the mill is always operating at optimum speed.
Right, so let's give this a go. So if I turn this winch, it's going to turn the gear system, transfer through here, and hopefully we'll turn this 8-ton cap above my head. Apparently, it takes about 20 minutes with someone stronger than me to turn the cap through 90 degrees. I don't think I'll last that long. I'm currently shifting 8 tons with this. Oh, feels like it too. Oh, there's no way I could have been a miller.
Ramelli's designs were instrumental to the development of the roller bearing, an innovation that has helped shape the modern world.
The roller bearing is an essential engineering component that most of us just take for granted today, but it's used in manufacturing, in construction, in the energy sector. The world around us will be a very different place without this ingenious component.
From a 17th century mill to the biggest and most advanced ship crane in the world, the team behind Sleipnir
This roller bearing is the biggest in the world.
will need to take Ramelli's idea and supersize it.
When you see it rotate for the first time, it's really impressive.
17th century visionary Agostino Ramelli inspired the roller bearing system that makes the remarkable rotating cranes on Heerema Sleipnir possible. On board the Sleipnir, Yori is getting up close to the world's largest incarnation of Ramelli's innovative technology.
So now we are inside the crane top, which is the connection piece of the vessel to the crane. And next to us, we see the roller bearing, which makes it possible for the crane to rotate. This roller bearing is the biggest in the world and has a diameter of 30 meters. It's really a unique piece. So the whole roller bearing is built up from segments, and within the bearing there are 5,000 small roller elements that make it possible for the crane to rotate.
The bearing consists of 2 rings. The lower section is connected to the vessel, while the top is joined to the bottom of the crane. When the rollers are added, the system allows 360 degrees of rotation.
In the past, on similar cranes, bogie wheels were used, where the crane rotated on like a train track. But that means that you will use a lot of steel and reinforcement. So by going back to the roller bearing design and just expand the size, we made it possible to rotate the whole crane, which weighs 9,000 tons, very smoothly on the bearing. And actually the crane can rotate within 2 minutes.
By implementing the roller bearing system, the team has made it possible for the 2 main cranes on board to be able to lift more than they weigh.
When you see it rotate for the first time, it's really impressive.
Alongside the roller bearing, over 40 miles of steel rope allows the Sleipnir to lift loads 420 feet into the air, allowing giant structures to be built at sea faster than ever before. And floating off the coast of Israel, Sleipnir recently attempted her toughest lift to date. After days of planning and positioning, a vast platform weighing a massive 16,860 tons was successfully raised. And then moved into place, setting a new world record for a floating crane lift.
Yeah, it's incredible. You hear the engines, you see the boom going up. And it's just amazing.
Engineers may have built the two most capable cranes at sea, but now they face their most important challenge.
Safety of the crew on board is the most important thing to us.
But keeping up to 400 crew members safe in these difficult conditions is a major challenge.
We are exposed to different risks. We work on a ship that moves. It's at sea, so you can have bad weather. We lift very, very heavy things. We work with heavy equipment. We work with big cranes. So we are exposed to a lot of different risks that you won't face on shore. If we have to abandon ship, then we are faced with a big problem. Because getting people off a ship at sea in an ocean is one of the more difficult things there is.
It's a problem that's made much more difficult when your deck is situated over 100 feet above the waterline.
Jumping in the water from this height or this ship, that's really a last resort. The absolute last resort.
So could a life-saving solution lie in the innovations of the past?
Launching in 5, 4, 3,
2, 1,
launch.
The Heerema Sleipnir, a billion-dollar heavy-lifting crane megaship, capable of traversing the planet's oceans and lifting the equivalent of over 30 A380 passenger jets. It takes up to 400 crew members to operate this monster vessel, and in the event of a disaster at sea, they need a way to safely escape. But with the deck often situated up to 115 feet above the water, the usual lifeboat launch system isn't an option.
Stand clear.
In Cork, in the south of Ireland, Deck Officer Stephanie Hyde is discovering another mechanism that's been in use for over 100 years. It offers an alternative to open-top lifeboats that are lowered mechanically. On a vessel as big as the Sleipnir, the time it takes to discharge a lifeboat using a winch could be the difference between life and death.
This type of escape system obviously works, but as ships and facilities got larger and even more dangerous, engineers had to find a system that got people faster and farther away from danger.
Luckily, one man was working on a solution. In the 1960s, Dutch marine engineer Joost Verhoef designed an ingenious new system for saving lives at sea.
So this is what Verhoef came up with. It's a fully enclosed, free-fall lifeboat.
By opting for a gravity-powered launch, Verhoef's design was capable of getting people to safety faster than ever before.
When the ship is at sea, this hook here is the only thing keeping the boat secure. Once the coxswain pulls the release handle, this hook will go up and release the lifeboat into the sea and away from danger.
And by fully enclosing the boats, escaping crews were protected from fire and any falling debris.
So this is the inside of our free-fall lifeboat. On my right-hand side here, we have the coxswain seat, where he can start, stop the engine. It also has its own self-contained air system. So in the event of the ship being on fire, we'll be able to breathe in fresh air rather than any toxic gases or smoke
which may be coming from the outside environment. The great thing about this design of lifeboat is that it's much safer and it's much more efficient. As soon as you press the release handle, you're in the water and you're away from danger straight away.
But this increased speed of launch creates a problem when the lifeboat meets the water.
When the coxswain is happy, you'll pull the lever and release the lifeboat, which will travel at a very high speed into the water. It is possible that it will capsize, but there's a ballast system in it that will ensure it always rights itself afterwards.
Situated in the hull of each boat, liquid-filled ballast tanks and buoyancy foam ensure that however the vessel hits the water, it always rights itself to the correct position. To understand the engineering brilliance behind Verhoef's design,
Okay, I'm all strapped in.
Stephanie is strapping in for a brief but extreme ride.
Oh, I'm so nervous. The door is closed, so we're almost ready to go.
Launching in 5, 4, 3,
2, 1,
launch.
Oh my God, that was unreal. We went fully under the water. We can now get away from danger really fast and safely. You see, within seconds, we're about 100 meters away from the jetty already, much faster than if we were using the open lifeboat. It's tough, can be used in all weather, and most importantly, it gets you out of danger quickly. That was so much fun. What an amazing piece of engineering.
This pioneering lifeboat system has been in use on oil rigs and large merchant ships since the 1980s. But to outfit the Sleipnir,
Of course, we hope that we never have to use these boats for real.
engineers will push Verhoef's innovation to its limit.
Because no free-fall lifeboat has been launched with people from this high up.
Inspired by Dutch inventor Joost Verhoef, the free-fall lifeboat system on board mega crane Heerema Sleipnir is one of the most advanced in the world. Should Arjan and the crew need to abandon ship, a fleet of free-fall lifeboats is ready to ensure their safety.
We are here at lifeboat station 1, 2, and 3. And what you see here are our free-fall lifeboats. Our means of escape in case of an emergency. If we launch this lifeboat with people inside, we would be breaking a world record. Because no free-fall lifeboat has been launched with people from this high up, which is about 55 meters at the moment.
Located above the deck, 9 free-fall lifeboats, with space for a total of 630 people, are ready to launch 24 hours a day.
Of course, we hope that we never have to use these boats for real. We only exercise with them. We don't want to use them in real life.
Each lifeboat is equipped with the essentials to survive at sea.
These lifeboats come equipped with quite a few things. There's water inside, there's food inside, there's also fishing tackle inside. There's means to rescue, to alert people, there's a radio. We have fuel for the boat for 24 hours, so we can sail actually about 150 miles from location. I've never been on board in a free-fall lifeboat, but what I understand from those who have, it is quite a roller coaster ride.
It's a feat of engineering few thought possible.
Sleipnir for me is really a mind-blowing vessel. Seeing the cranes working that I have designed makes me really proud.
by looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
I'm a naval architect, so you can imagine that building such a big vessel for a naval architect is like a once-in-a-lifetime dream. I'm really excited about the whole thing we've done with Sleipnir.
Engineers have constructed something radical